that you're going to want to, that's going to affect stuff moving forward, okay? So we're going to look at some theory today, all right? And we're going to start off basically by saying, defining what the definite integral is. And basically how to make, so definite integrals. So if you remember, the indefinite integral, written up over here on the whiteboard, was just f of x equal, the integral of f of x dx equal the antiderivative of f of x plus c, okay? Definite integrals are different. We're now going to define with the definite integral the interval on which we're looking at, okay? So the notation for it is going to be the same as it is for an indefinite integral, except you're going to get numbers now, a and b, along my integral symbol, okay? Yeah, so this would be like 1 and 5, or something like that, okay? Or like 0 to 70, or minus 80 to 2, or something, okay? And the definite integral is going to be equal to, here's the big difference. The definite integral is equal to the antiderivative evaluated at b minus the antiderivative evaluated at a. Okay? And so that's what the definite integral looks like. Okay? Any questions about that? So essentially, you're taking the integral and then you're plugging in the numbers, but when you plug in the numbers, you're doing the difference between the antiderivative of the top number minus the antiderivative of the bottom number. Okay? Any questions about that so far? Okay, good. One thing, excuse me. One thing this definite integral models is the area bound between the curve and the x-axis. Okay, so its use is to find the area, or models, between the x-axis and the function. Okay, so that's something, basically, that's its primary use. That's its actual, original use for this thing, okay? Just like the derivative was mainly used to calculate instantaneous rate of change, or basically the slope of the function on a point, this is doing the area underneath the curve, or the change in the function over a large interval, basically, okay? So instead of doing it on a point, it's the change over a zone, if you will, okay? Everyone got that? That's what the definite integral models, okay? Now, how it does this specifically is what we're going to be looking at today, okay? And it's going to take some new notation that you guys haven't seen yet, and working with some things and things that nobody really likes to do, okay? But let's go ahead and start that. So to understand how it models that, we're going to start off by talking about summation notation. Or sometimes referred to as sigma notation, okay? Now, what sigma notation is this is basically what you write when you're adding up a string of numbers together, okay? When you're adding up a series, and what a series is just numbers being added together, but they follow a distinct rule, so it's like a function, but you're adding every term of the function together, okay? Use this sigma notation. So the idea here is it might be something like f of 1 plus f of 2 plus f of 3 plus all the way up to some last number f of n. And we would write this series as sigma from our first number to whatever our last number is of the function, where that x of I there is just a placeholder. It's basically holding the place for whatever number I'm going to be inserting for this time around. Okay? So let me give you an example of what this would actually look like. okay? Suppose I wrote out for you the following. Let's do from I equals 2 to 7 of, 7's a little big. We'll keep it simple. Of 3i squared. If I'm writing out what this sum is by hand, it's just going to be 3 times 2 squared plus 3 times 3 squared plus 3 times 4 squared plus 3 times 5 squared plus 3 times 6 squared, finally plus 3 times 7 squared. That's all the summation notation means, okay? So everyone got that? So this is just kind of an example of how this works out, okay? Of how you understand how this thing.
So the top tells you where to stop.
Top tells you where to stop. The bottom number tells you where you start, okay? And then the function on the inside just tells you where you're sticking that number in, okay? So in this case, the I there, notice that was the only thing that changed there, okay? The 3 did not change. We didn't do anything with the 3, just stayed a 3, okay? The square didn't change, just remained square. The only part that was changing was the I, and that just changed from starting my first number 2, in this case, going to my last number 7. You just go up by one natural number every time, okay? That's how these series work, and that's how sigma notation works, okay? Any question about how that works? Okay. Now you might be asking, what on earth does this have to do with this integral over here? What does this have to do with definite integrals? How this affects definite integrals comes about how the definite integral models the area underneath a curve, okay? And so that's what we're going to look at next, modeling the area underneath a curve. So if we got this down, we could go ahead and move on. Everyone have this copied? Cool. Okay. So, okay, so if I'm doing the area underneath a curve, okay, I'm going to go ahead and draw a random curve up here, like so, okay. We'll do this parabola-looking thing. This is where, we'll call this our first point. It's at the origin. We'll just call this point A here. We'll call it what crosses again over here, B, okay? And I want to go ahead and find the area underneath this curve, okay? Without knowing how the definite integral works or anything like that, if you were just given this problem on your own and say, figure out how to find the area of this curve, what would you guys do? What could I do?
Turn it into a circle.
Okay, so you might try to find a geometric shape that matches it up. And this thing looks like it might be part of a circle, so maybe that would work. Maybe I could find a geometric shape that lined up with it nicely. But I'm going to tell you right now, this is not part of a circle. This is a parabola. While they curve, circle ain't going to do it, okay? But what else could I model it with?
Rectangle.
I could divvy it up into rectangles, right? I'd come through here and say, okay, let's partition the bottom out. So we'll call this x1, x2, x3, and we might want to be smart and make those all the same size. And then I can draw this out. I can use rectangles, okay, to model out my zone, like so, right? Okay? Well, that's well and good, and that'll give me a nice approximation of the area on the inside. But does it do an exact job? No, because look what's happening. Right here, I'm adding all this extra area, but on this side, I'm leaving out these large areas. In fact, this side, I don't even, because it goes, the last rectangle here is actually a flat line, that whole area down there gets left off. So with my 4 partitions here, I'm either adding too much area with my rectangles or taking too little, okay? So how would I go about fixing that? What would I do?
Or using sigma notation.
Smaller rectangles.
Smaller rectangles, right? The more rectangles I have, the better the approximation is, right? Okay? Huh?
Why can't you do like a trapezoid?
Actually, there's a form, there's something called Newtonian approximation, which uses trapezoids. We're going to learn that one later, okay? going to stick with this. But you're absolutely right. If I use smaller rectangles, okay, and use a whole bunch of smaller rectangles, I can get this thing to be closer and closer and closer to the area underneath the curve. Okay, so that's one thing I could do there. But before we go ahead and do that, though, how would I model the area of each of these rectangles? Okay, what would I do? The width of each rectangle would be determined by what?
Between points.
The distance between points, right? So for my first rectangle, it would be the distance between x sub 1 minus a. For this one right here, it would be x sub 2 minus x sub 1. This one would be x sub 3 minus x sub 2. And this one here would be b minus x sub 3, right? Okay? If I'm making, since I want to make all those partitions the same size, okay, I can actually write a little formula that would model that better, okay? And that formula would be b minus a divided by n, where n is equal to the number of rectangles I want. Okay? Come on. The number of rectangles I want, okay? So in this case I would have 1, 2, 3, 4, so I do b minus a over 4. That would be the size of each partition. By the way, we're going to go ahead and replace this, give it its own special variable. We're going to write it as a delta x, okay? And so the change in x, that is the width of each of these rectangles, is determined by this little formula up here, okay? So that gives us part of our rectangle formula. What's the other part we need? We've got the width, we need the height, right? How can I find the height of each of these? What would I do? Isn't this thing a function?
Yes.
So couldn't I do the function just evaluated at whatever point I'm dealing with?
Yes.
So like for my first rectangle, I would do it as the change in x here, so delta x times f of x sub 1, right? And that would give me that guy right there. So I could write that that one there is delta x times f of x sub 1, okay? The second one would be delta x times f of x sub 2, right? This third one would be delta x times f of x sub 3, right? And this final one, this bottom line one, would be delta x times f of b in this case, okay? So that's one way I can model it out, okay? Do I necessarily have to make my rectangles like so? Is there another way I could have done them? So I chose to make rectangles based off of the bigger number in the interval, right?
More intervals.
Okay, well I can add more intervals, and we will do so. But I could do what? I could choose the lower number in the interval, right? That would give me a different set of rectangles. So I might have one, so my first one again is going to be kind of flat, but then I'd have one between these two intervals, it would be that rectangle this time. Between these, it would be that rectangle in blue, and between these, it would be that rectangle right there.
The two.
Okay, well that would help give me a closer, better approximation, but as it currently stands, it's not going to, again, perfectly give me the area underneath that. But it does give me a slightly different approximation. And my area formulas would change, right? Well, that's by purpose. That's always going to happen when you do a rectangular approximation this way. In fact, the first one I did it, the one in, I'm guessing in green, that way is what's known as an upper sum, and the one in blue is a lower sum. Upper because I'm using the larger of the two numbers to make the height of my rectangle. Lower because I'm using the lower of the two numbers. So the upper sum in this case, I can write it as delta x times f of x sub 1 plus f of x sub 2 plus f of x sub 3 plus f of b. Okay? And the lower sum I can write as delta x times f of a plus f of x sub 1 plus f of x sub 2 plus f of x sub 3. Okay? And so, note, these are both basically using the same exact rectangular system, but one's with the upper end of the zone, basically the higher endpoint. This one's with the lower endpoint, hence upper and lower. Okay? But notice here, what these things become. These are what? They're series, right? I can replace them with sigma, right?
Alright.
Okay? And in fact, if I do this in the general case, with lots of different rectangles, okay, what I would write is, I would write all that out. I would have my delta x times my first one, okay, plus my second one, plus my third one, all the way up to whatever the one I did in the end, the nth one. And I would write this as the sum from I equals 1 to n of f of x, of delta x times f of x of I. Okay? Like so there. Okay? And so that sum is the general sum for doing that rectangular method I just did. Okay? Now though, we've already established this is all well and good, but if I have a finite number of rectangles, am I going to get the exact area? No. I'm going to need a lot of rectangles. Okay? And I'm going to want as many partitions as I can possibly have. Okay? So I'm going to want an infinite number of partitions, right? Okay? That's a lot, isn't it? Okay? But what happens if I make the rectangles an infinite, if I put an infinite number of rectangles? How wide do they become?
Infinitely wide.
No. Quite the opposite.
Small. Zero.
Almost zero, right? What tool can I use to get things arbitrarily close to something else?
Limits.
The limit. Good. And in fact,
Possible.
how this thing becomes the definite integral is I end up taking the limit of this as
Doesn't
n
exist.
goes to infinity
Well, this doesn't exist.
Exactly.
of this thing right here.
Mean Girls.
Mean Girls. They got it right, by the way, Mean Girls.
Wait, did you actually know that equation?
Whatever the, I can't remember what equation to do off the top of my head, but someone wrote it down for me once and gave it to me and said, what's the answer? And I was like, the limit does not exist. Which apparently is the answer they gave in Mean Girls.
Have you
Okay.
ever seen
gotta do the- you gotta do
Wizard
the-
of Oz when they're just like so bad at they like get the
Yeah, that's part of the joke, actually. Yeah.
What did you?
He butchers the Pythagorean theorem.
Well, this makes no sense.
Is this about as hard as it's gonna get?
What
This stuff?
Yeah.
This is calculus.
Okay. And
Could
so
this be on the AP exam?
knock it down?
it can be. Let me explain how it can be on the AP exam though. There's two ways this will show up.
Throw my test in
Okay.
there.
No. Don't throw your test in the air, and don't freak out about it either. How this would show up would be sort of the same way we saw with that multiple choice question, where you'll be given this ridiculous looking like limit, and it turned out just to be the derivative. Same thing here. You'll be given a ridiculous looking sum, and it just turns out to be the integral. Okay?
Interesting.
And remember, delta x is equal to b minus a over n. So they could replace delta x with whatever, so it could be like 5 minus 3 over n times this function, and you're doing the sum of it as n goes to infinity. If you solve that, don't be like, oh my god, it's awful. No, it's just this right over here.
So we just did all of that to show why that is
Uh-huh.
the case.
But also explain how it could come up in practice, okay? Because it does come up on the AP, again, it does. In fact, actually what you're much more likely to see, everybody, on the AP test is problems where, with actual numbers involved,
I heard the Tommy
where you're doing
calculus, so he's there.
the rectangle sum up. And in fact, for homework tonight, you've got a few problems where you're given a curve or a function, and you're told, add together all the rectangles beneath it, okay?
And then,
Basically do this, okay?
and so,
And to approximate the error,
Infinity.
okay?
so if we just have the, we just take the derivative of that.
Sorry, what's your question?
So,
No.
If it's gonna do something like this,